Right, so today we are ready for the lecture 11 slide set. So it has been shared on LMS with the previous lecture slides 9 and 10. In recursion, so as I remember, like lecture 10, it is on recursion. So I will like you can follow that, like you can go through that. So next week, so if I get some additional time, so I will go back to lecture 10 slides and I will discuss those things, the main points of recursion. Right? So today we are going to go with lecture 11 slides, which is on binary trees. Okay. So have you heard of binary trees in your A levels? So before this lecture, have you heard or have you used binary trees? So any of you? Johan, have used. Where did you use Johan? All right, okay. Not binary tree, but tree passing. Okay, okay. Yeah, passing mathematical expressions. So trees are used. Right. So anyone, so can you raise your hands? So if you have used binary trees, if you have learned about binary trees before, can you raise your hands? No one? So Johan, you can raise your hand. Right? No one? Okay, right. So no problem. Right. Okay. So no worries. Let's start with the very basic level. So I'll explain all the things on binary trees. Right. Right. So binary trees. So the idea, the original idea came from the real trees that we see, right? So so if you see a tree, like there are roots and then trunks and then leaves, right? It's like so we have a general structure, like different trees having different structures, but generally we can identify this is a tree, right? So based on that idea, generally not just binary trees, like we have trees, right? So binary trees are a special case of a special set of trees, right? So tree data structure has been introduced with that idea, right? So let's see why we need trees, right? So we have already learned several data structures, right? Like we have arrays. Arrays are very important, and performance-wise, those are the best, right? And then so we have linked list. Linked lists are very important and very flexible. So you can insert and remove items without restrictions, right? Linked list. And then we learn, so these are considered as like primary data structures or elementary data structures, and then so we have secondary data structures, right? More abstract data structures like stacks and queues. So even under queues, like we can find priority queues. Priority queues. But we have many data structures. So we have learned several data structures so far. So then what is like with performance wise, we have arrays, right? So then if we need some flexibility, we have linked list, and then some special requirements, we have stacks, queues, priority queues, and so on. So then why we need a new data structures? Why new data structures? Right. So first, let's discuss that, right? So when you are going to discuss something, so first we have to discuss whether it is necessary, right? So right. Actually, the reason, if we want new data structure, if we are going to introduce new data structure, so there should be, it should be a solution for a limitation that we have with other data structures, right? If we have some limitations with all these data structures, if there's a gap of these data structures, right? So with arrays, we can access items if you know the index. So we have the flexibility with linked list. And then, so others, they have their special features. So they have their advantages, as well as we can identify their disadvantages. So there are a lot of disadvantages that we have identified. So can anyone tell me one disadvantage of array? Fixed size, yeah, very good. And then one disadvantage of linked list. No random access, yes, very good. Likewise, so we have disadvantages as well, right? So then, based on those disadvantages and some limitations, right? Some limitations. Right? That's where we have to go for some other solutions. Right? That's where new data structures are introduced. Right? We are not going to stop at trees. So next semester, we are going to learn some other data structures. Right? Like hash tables. Right? So let's see why we need trees, why we have to go for trees. Okay, right. So if we take arrays, so if we take arrays, insertion, right? So if we take ordered array, sorted array, if we are going to insert a new item there, so basically the size is fixed, right? Size is fixed, so insertion would be not possible. And even if you arrange something, if you are going to fake insertion, right? But even in that case, inserting, right, in arrays, inserting new item is not a very convenient operation, right? With arrays, insertion is a problem. Right, like so basically size is fixed, insertion is impossible if array is full. If array is full, we cannot insert new item, right? Suppose array is full, we cannot insert, it is not possible. And in some cases, if it is ordered array, even if it is not full, right? If you're going to insert a new item, so you have to check the order. Right? So there are a lot of steps that we have to follow. So you have to insert somewhere, and then other items may have to be shifted. So shifting is not a it is not cheap. It is very expensive. We have to spend a lot of steps, right? So we have to use a lot of steps to do that, right? Likewise, in this example, so we are going to insert 23, right? It should go in between 12 and 26, right? So if array is full, so you may have to create a new array and insert these items one at a time, and then you have to insert 23 in between 12 and 26 or something. It is not convenient, basically. Slow insertion. We can do that, but it is slow. Okay. And then when it comes to the linked list. So if you are searching, so if you remember, so we learned searching in a linked list. So if you have a linked list, if you're going to search something, right? Search key. If you're going to search any value, so only way that you can do searching would be linear. Linear searching would be possible. So the searching is slow. In linked list. So in linked list. So in arrays, insertion is slow, right? So if you want to insert fast, so then don't go for arrays, go for linked list. Can insert කරන operations ගොඩක් වැඩි නම් ඔයාගේ application එකේ ඉක්මනට insert කරන්න අවශ්‍ය නම් performance හොඳට තියෙන්න ඕන නම් insert කරද්දී don't go, in that case don't go for arrays. If you need a fast insertion in your application, don't go for arrays, go for linked list. In your application, if you need fast searching, right? So then don't go for linked list, go for arrays. Go for ordered arrays, right? Ordered arrays or sorted arrays, right? So here, sorted array. Ordered, sorted array. If you need fast searching, go for sorted arrays. But what if you need fast searching? And if you need fast insertion, if you need fast searching and fast insertion in your application, we need both. If it is just one, we can go with our previous data structure. If it is fast searching, we can go for sorted directs. If it is fast insertion, we can go for linked list. If you need both, then we cannot get any help from these two data structures, right? So that's why we introduce a new data structure. Trees. So in this case, like there are different types of trees, but in this case, for fast searching and fast insertion, so we introduce a special trees like binary trees. Binary trees. Sometimes we call it binary search tree. So here, I think this part is a bit familiar. What is this? If we call binary search tree, this binary search, what is that? Have you heard of that? We learned two algorithms. We learned two searching algorithms. What are those two searching algorithms? So anyone? Yeah. So binary search and linear search. So the binary search, we learned binary search. So in this name, so we have binary search. Is it to do with binary search? So let's find out. Right. So anyhow, so if we call binary search tree or binary tree, right? In our context, if we just trees, so in this level, we only learn binary trees. Some trees කියලා කිව්වට ඒ මම කතා කරන්නේ binary trees ගැන. Right? But in a real like definition, this is not like binary search tree, binary trees, not the same in that case. Huh? Trees, so it is a vast area. So if I call binary search tree or binary tree, so we are talking about the same thing. Same thing. Right. So if we talk about trees, right? So like if this is all the trees, right, these are binary trees. It is a subset of trees, general trees. Okay. Right. So slow insertion and slow searching in arrays, ordered arrays and linked list. A data structure with quick insertion and deletion. Right? Not only insertion, but deletion as well of a linked list, quick searching of an ordered array. Right? In ordered array, so we can have quick searching. We have binary search, and then in a linked list, we can insert and delete items or the nodes easily. If you can combine these two, so we can have trees or binary trees. Trees provide both these characteristics. Okay, right. So let's talk about binary trees. Binary trees are one of the fundamental data storage structures used in programming. So trees are very commonly used in many situations, in many algorithms. Binary trees are used. They combine the advantages of two other data structures, ordered arrays and linked list, as we have discussed. Search a tree quickly as an ordered array, insert and delete items quickly as with linked list. Right, so let's go for the definition. So any questions up to now? Anything to be discussed or anything, any concerns? Right. So what is a tree? A tree is a subset of more general category called graph. Right. So then I told like we have trees and then we have binary trees. Then actually so we have graphs. Right, so these are graphs. So next semester we are going to learn graphs, right? Trees are a subset of graphs. And then the binary trees are a subset of trees. Okay. Tree is a subset of more general category called graph. In computer programs, nodes often represent such entities as people, car parts, airline reservations, and so on. Right? So, like any of these data structures, like arrays, trees, graphs, right? So their main objective, their purpose is to store some data. Right? So they store data. The data could be different types. That's a different concern. So, however, so their main purpose is to store data, right? or even trees. So their main purpose is to store data. Okay. So in that case, definitely, so there's a way to store data. So if it is an integer, so there's a place to put that integer values, right? Like if you remember in a linked list, so we used a special unit called a node. In this node, so we maintain one variable or one place to store the value. It doesn't have to be just one value. So in this unit, you can have multiple values as well, right? So you can insert one or multiple data, right? So these are data. And then additional place to store the next, the address of the next node. And in a doubly linked list, so we need another additional place to store the address of the previous item, right? So this is the basic structure of the unit, the unit which is used to build or construct a linked list, right? So we use the same idea in trees or binary trees. We use the same idea. We introduce a special unit. Even in this case, we call it a node. Right? So definitely there should be a place to store data. Right? It is there. So apart from that, we have some other things. So that's what we are going to learn. Okay. So usually tree so if you take a tree, not in computing but in nature, so we can see trees, right? So if we have a tree, so we have right. So we have roots, and then we have branches, and we have leaves, and so on. So when it comes to computing, in our trees, we have roots as well, right? We have a root, and then we have branches, and we have leaves. Right? So, however, in this case, in our trees, root would be on top, right? Anyway, so if you arrange this tree upside down, then roots go here, right? Right. Make it upside down, then roots would be on top. Actually, I mean, in the real world, even in like modern agriculture, so there are some methods of growing plants in special containers, right? So in that case, the roots would be on top, right? So I don't remember the name of that. Like if you are interested in agriculture and all, so there are some ways that you can grow upside down. Roots would be on top, and then I don't remember actually the name of that method. So I have seen that in even in Sri Lanka. So I have seen that in BMICS. So there was a exhibition few years ago, like the University of Sri Jayawardhanapura. So we participated in that. So there was some stalls. So they displayed so those methods. So anyhow, like in our computing, root would be on top, right? And then, so we have branches. And then those branches are connected to other nodes. So usually we call nodes, right? So we have nodes. So these are the units that we store data, right? So nodes. And then we have a root, one root. And then, so there would be several branches. So these are called branches. So we have some other names, like just for the introduction. So I use that. And then the bottom level, the last layer, right? If this tree is up to this, so these are called leaves. These are leaves. There are no branches. These are leaves. All these nodes are containers of data, right? So we can store data in these, even in leaves, so we can store data. So those are data storing units. So nodes are data storing units. Later on, we can talk about the structure of a node, right? Somehow this is. So each node is connected to one or multiple other nodes. So this one is connected, the root is connected to this one, and it is also connected to this one. And then if we take this node here, it is connected to another 3 nodes. This node is connected to another 4 nodes. So likewise, nodes are connected. Right, so if we take a linked list, so one node is connected to next node. The other way, like next node is connected to the previous node. Likewise, so we have connections between, right? It's like a chain in a linked list, but in trees, it is more complicated. In linked list, it is linear, but in this case, it is more two-dimensional, right? In linked list, the connections go just in a linear manner, right? This way or that way, right? සරල රේඛාවක වගේ තමයි ඒකේ connection එක යන්නේ, chain එකක්. But in this case, the connections goes in 2 dimensions. It goes this way and this way, like 2 dimensions. So in computer programs, nodes often represent such entities as people, car, parts, airline reservation, and so on. Like these nodes, this data would be related to anything like car information, right? If you're going to store car information, so then car information would be in all these nodes. One node would represent one entity, one car, right? So I don't know. I mean, in this case, cars are not, may not be very a good example, right? So anyway, this node, like we store different types of data. They could represent people, car parts, airline reservation, but whatsoever, like nodes can store those data. So then we have lines. So I told you, so the branches. Actually, so we use a special name for that, edges. So lines that connect, the connections between nodes are called so in this case I use branches for the easiness, but they are called edges, right? So in computing, so we use nodes nodes, and then nodes represent different entities, and then edges. So even in trees, even in graphs, in both cases, we use this concept. So graph is something like this, right? So we have different nodes, and then those nodes are connected. Sometimes one node is connected to another two, or like multiple nodes. So this is a graph. Here, so these are nodes, and then we have edges. Nodes. And we have edges. Right, different edges. So even in trees, so we have nodes, and edges. Nodes and edges. All these connections are edges, right? So even these three would be edges. The lines between the nodes represent the way the nodes are related, right? When we visualize the trees, or even trees, or graphs, or even linked list, so these edges, so these are connections, or these are how these nodes are related. For example, if we take, suppose if I number these nodes, if I number these nodes, suppose this is node 1, this is node 2, this is node 3, right? For example, node 1 and 2 are related. They have a connection. Node 1 and 3 are connected. They have a connection. But node 2 and 3 are not connected. They don't have connection. They are not related. Right? The lines, edges between the nodes represent the way the nodes are related. Convenience of getting one node to another. It's another way of saying that, from node 1 to node 2, we can go because there's a connection. From node 1 to 3, we can go. But node 2 to 3, we cannot go directly. If we want, so we have to use some other way. Okay, so that's the idea. Convenience of getting one node to another. The node at top of the tree is called the root. There's only one root in a tree. There's only one root in a tree. So one and only root. If we take a real tree that we can see in the nature, so there are many roots, right? There are many roots, several roots, but in our case, in computing, there is only one root in a tree. Connected nodes between, so below a given node are called its children. Connected node below a given node are called children, right? So if we have a root here and then connected node below, right? Below, for example, so there are two nodes here connected. Connected node below are called children. Right? So let me remove all these additional things. Right. So let's go with a clean. Right. So we have 1, 2, 3, 4, 5, 6, 7, 8. Right. Okay. So I have numbered these. No. So node 1 is the root. Right. So this is the root. Then nodes connected below. So nodes connected to root. What are the connected nodes to root? 2 and 3 are connected node below. Are children of node 2 and of root. So if we take 4 and 5, are they children of root? That's the question. The question is, are 4 and 5 children of root? Anyone? Yes, but not direct. connected nodes below a given node are called its children. Right? Children means connected nodes, right? So then 4 and 5 are not connected to root, as Johan says, directly not connected to root. So those are connected to root through 2. Right? මේ 4යි 5යි මේ කට්ටිය directly connect වෙලා නැහැ අරයට. එයා connect වෙන්නේ 2 කියන node එක හරහා. So we cannot say 4 and 5 are children of root. But we have a special concept called grandchildren. Grandchildren. So 4 and 5 would be grandchildren, but not children of root. එන 4යි 5යි root එකේ ළමයි නෙවෙයි. හැබැයි root එකේ ළමයාගේ ළමයි. හරි? ඒ වගේ. Right? So these are words like we can so I'll explain all these terms that we are using in these trees, right? Right? So here is the tree terminology, right? So we have roots. So we have one and only root for a given tree, right? So then we have children, and we have parents, the opposite of that. For example, node A would be the parent of node D and C. Right. So we have child or parent relationship. This is 1, 2, 3. 1 is the parent of 2 and 3. The other way of saying that it would be 2 and 3 are children of node 1. Two is a child of 1, 3 is a child of 1. Right? So here B is the parent of D and E. D and E, their parent would be B. So sometimes we call left child, right child, right? So I'll come to that one later on, right? So in this case, if there are only two children, D is the left child of B, E is the right child of B. So the left side child, right side child. Right? Then we can identify levels as well, right? So usually we name root level as level 0, right? So then we have level 1, the level of the first children of the root. And then their children would be in level 2 and so on, right? Sometimes we call them generations. So this is the 0 generation. So generation 1, 2, 3 and so on. අර පරම්පරාවක් කියලා අපි කියන්නේ. අපේ පරම්පරාව කියලා අපි කියනවා. ඊට පස්සේ අපේ තාත්තලාගේ පරම්පරාව. ඒ වගේ අර මේ උදාහරණයක් විදියට so for example, like, so if you have, so if, suppose if your grandfather is having, right, 3 children, right? So suppose your father or mother, right? It doesn't matter, right? 3 children. So then, so your father or mother will have, suppose there are two children. And then your uncle or aunt may have 3 children. Right. So this is one generation, right? Right. So your generation you share with your brothers or sisters or with your cousins, right? So in our case, so we call them level 0, level 1 and so. Right. So still we are talking about the structure of a tree, and then later on let's see how trees can help us with fast insertion and fast searching. Okay. And then another terminology that we use here would be subtree. Right. Subtree. So subtree is right? So we have a tree, right? If we can identify a tree structure within a main tree, right? So if we take this part, it is again, if you forget about other parts, right? So let's take this part separately, right? Just forgetting the other parts. Like if we take this part separately, it has a tree structure itself. So this would be the root here. Right? If you remove other parts, right? So then this exhibits a tree nature itself. Right? So we call them subtree, right? So we have a subtree here. So we can see another subtree here. So if we have a complicated tree like this, so if we take so if we have, so we can identify a subtree. We can identify another subtree here. So we can identify a subtree here as well as a subtree here. So even if you consider just one node, it is also a subtree, like with a tree with just a root. Right? So likewise, in a one tree, we can identify several subtrees. Okay. And again, so we have something called a path. Path. Path means if you can move from the root to some other nodes with the connections they have. So that is a path. The roots or the nodes that we have to follow, right? For example, if I want to go from node A to node J, so then in that case, I have to go, first I have to go to node C, and then I have to go to node F, and then I have to go to node J. So if you go from A to B and B to E, so then we cannot go to J. Right? A, B, E කියන පාරේ ඇවිල්ලා අපිට යන්න බෑ J එකට. J එකට යනවනේ යන්න තියෙන එකම පාර A, C, F, J. So that is called a path. Right? So these are the main tree terminologies. So there are some other terminologies as well. Right? So I'll come back to these three terminologies again. So these are the basic ones, and then with some definitions, we can identify the terminologies. So I'll come to that later on. Right? Okay. Right. So first, let's talk what is a tree and what is not a tree. Actually, this is not a tree. So why is that? Yes, very good, Akila. And then Saran, Vajira. Children have two parents, yeah. So if you see node H, so node H has parent D as well as E. Yeah, that's a problem, right? So if it is a tree, in a tree, one child cannot have two parents. So even in, if you see node J is having two parents, F and G. It is not possible in a tree. So that's the difference between a graph and a tree. Graph and a tree. I told you, graph is a big set, and inside that we have trees. So this is trees. So this is graphs. Graphs, we don't have any restrictions, right? Any node can be connected to any other node, no problem at all, right? No limitations. But when it comes to trees, a special case of graph, so how trees are different from graphs, so that's where, so one node, right? One node right? Cannot have multiple parents. And the other thing is, if we in a any graph, if we identify a root, right? From root to any other node, right? If we take any other node, right? There should be one path. But in this case, there are two paths here. From root to any other node, there should be only one path. So even in this case, if you want to go to J, if you want to go to J, from A to J, you can go use this path A, C, G, J. Or you can use this path A, C, F, J. There are multiple paths to reach to one node from the root. right? If you have multiple paths, it's not a tree. It is a graph. It's just a graph. If it is a tree, so we have to follow that specific, right? Then binary trees. Binary trees. So again, I will emphasize the previous point. What is the difference between graph and tree? Tree cannot have multiple parents. If the parent, this concept is not in a graph, so in that case, we can rewrite the same idea with this, right? If you identify one node as a root, from the root to any other node, there should be only one path. Be only one path. So root to any other node, there should be only one path. So later on, so keep this mind, and later on think, is it only between root and other nodes, or is it for any two nodes? Right. Then my root කියන කතාව අයින් කරන්න. Right. From the root node. Right. If you remove this from any node to any other node, right? Check whether this is like later on. And මම කිව්වේ දැන් root එකේ ඉඳලා ඕනෑම node එකකට තියෙන්න පුළුවන් එක path එකයි tree එක. ඒක අදාළ වෙනවද කියලා පොඩ්ඩක් පස්සේ හිතලා බලන්න. ඕනෑම node එකක ඉඳලා තව node එකකට ගන්න. Whether it is true. So it is a question mark. It is for you to check. Right. So anyway, so let's go with binary trees, right? So here, if we take trees, right? So we have root, and then we have children. So we can have multiple children. So here, so how many children for this node? How many children? 3. For this node, there are 2 children. For this node, there would be 0. For this node, it would be 0. Again, for this node, 0, this node, 0. So how many children? How many children? How many children for the root? 3 children. How many children for this node? 2 children. How many children? Right. How many children? In this case, it could be, all right. So let me add another. Right. So here, so I'll change it to 1. It's 1. How many children here? In some cases, it is 0, no children. For some nodes, it is 1. For some nodes, it is 2. And for some node, it is 3. Right. To become a binary tree, so binary tree means any node can have maximum 2 children. If any node is having maximum 2 children. So maximum, we call it is a binary tree. So maximum 2 means it could be 0, or it could be 1, or it could be 2. That means, suppose a root is having 2 children, and then this one can have 1, this can have 1, this one can have 2, and so on. No 3 children. Right. So if so, we put we set up a law. Suppose in Sri Lanka, if we set up a law, anyone can have, any family can have only 2 children maximum. If you don't want to have children, it's fine, no problem. If you want to have 1 child, that's also fine. If you want to have 2 children, that's fine. But more than 2 children, so then you may have to pay some additional taxes. So if you know, like in China, I don't know whether it is still there. But China, they had a law. It could be still there. Like people can have only 1 child. If you want to have more than 1 child, then they have to pay additional taxes, special tax to the government. Right. So most of my Chinese friends, so they are just only child of the family. They don't have brothers and sisters. right? But if so people who's having money, so they can have more children. So that's one way that Chinese government control their populations, because they have a huge population, so they had to do something on that. So they introduce that law, right? In binary trees, we introduce this law. Any parent can have maximum 2 children. දෙන්නයි පුළුවන්. ඊට වැඩිය බෑ. If you want to have more than that, that's not possible actually. In binary trees, like in the Chinese government, if you want to have two, so more than that allowed, so then they can do that with paying a large amount of taxes. But here in binary trees, it is not possible, right? If you have more than 2 children, then it is not a binary tree anymore. Binary means 2, binary. So that's the idea. Binary means 2, maximum 2 children. So here we talk about binary trees in our discussion. We don't talk about trees with more than 2 children. It's not, it is out of our scope in this semester as well as next semester. So we talk about binary search trees, binary trees. Okay. If every node in a tree can have at most 2 children, the tree is called a binary tree. So maximum 2 children, or at most, the same idea, 2 children. The tree is called a binary tree. The 2 children of each node in a binary tree are called left child and right child. There are 2 children, left child and right child. Sometimes left child is not available, sometimes right child is not available, sometimes both are not available. That's also possible, right? So in this case, if this is A, B is the left child, C is the right child of A. A is having 2 children, but B is having only 1 child. B, okay, so if I name that as D, this one E, this one F, this one G. D is the left child of B. How about the right child of B? There is no right child. There is, it is empty. That place is empty. No right child. If we take D, what is the left child of D? No left child. No right child. No left or right child. No children for D. Right? The two children of each node in a binary tree are called left child or right and right child. A node in a binary tree doesn't necessarily have the maximum of two children. It may have only one left child, only a right child, no children at all, in which case it is a leaf. If there are no children, we call that node a leaf. Okay. So this is the definition of a binary tree. Any questions? Any questions? Right. Then binary search tree, right? So this is our path. This is our. So we talk about graph, right? Then graphs, some of the graphs would be trees, right? We identify how trees are different from graphs, right? So then from trees, how binary trees are different. Then from binary trees, so we have a special case of binary trees. We call binary search trees. Right? So that is our main concern. We are going to learn binary search trees. But however, in some cases, when I am using, I use binary trees, binary search trees interchangeably. However, they are different. Binary trees means at most two children. At most two children. Maximum two children. Graphs from trees, so we have only one path, right? Only one path from root to any other. Okay, so here and here, the next step. So what is a binary search? Binary search tree. In a binary search tree, a node's left child must have a key less than it is paired. Again, key. So don't worry about that. Like, so the key. Okay. So let's go to that one first. Binary search tree වලට එන්න කලින් පොඩ්ඩක් මේ key කියන්නේ මොකක්ද කියලා මම පැහැදිලි කරලා ඉන්නම්. So I'll explain the key first, right? So as I told you, in a node, right? Sometimes, in most of the cases, in trees, we indicate these nodes with a circle. But in some cases, we use small rectangle or a square, right? So anyhow, like nodes, they store data. They store data, right? In most of the cases, the data would be just one data, one value. So the key is key of that node. Key of that node is the value that we store. Value that we store. Store there. අපි එක value එකක් නම් මොකක් හරි මේ node එකක තියාගන්නේ ඒ value එක තමයි key එක කියලා. Right. So if we put integers there, so if we put integers, so then for example, if I want to put integer 12 in that node, so you can both use like circular or rectangular visualization, right? So no problem. So that's the key. And the other thing is, if you store multiple data, so if you store multiple data in a node. So for example, suppose if you are keeping, so if you have a class student info, so student may have a name, index, ID number, and so on. So if you store student info objects, right? So you can create an object from this class, student info object. So if you put this data in a node එකේ තියාගන්න මේ student info object එක. So then there are multiple data there, name, index, ID, and so on. From those data, you have to identify the key. Key would be, sometimes it would be ID number, or it could be index. One value to represent a multiple data. We store there. It can be decided based on the application. Application එකේ context එක අනුව අපි decide කරනවා අපි මේක තමයි key එක. So that would be the key. If it is just one value we store, that would be the key. If we store multiple values in a node, we have to choose one value to represent that. That would be the key. Right. So usually when we visualize our tree, so we put in this circular node, we put that key value, key. අපි store කරගන්නේ integers නම් මේ මෙතන මේ integers දාගෙන තියෙනවා. So that would be the key. Right. Okay. So here, any questions regarding the key? Another example would be, suppose if I have a class, student marks, right? So in that class, I may have like student ID or index, and then marks, right? So in this case, I may choose marks as the key, right? Then our actual node would be something like this, right? Our actual node would be something like this. In this node, so we have object, right? So we have marks, student marks object. So there we may have ID as well as marks, right? So the suppose student ID would be 25, the marks would be 83. So this is the marks. So this is the node. But when we visualize this node, we simply visualize it as this. 83. Right. So this is node structure is actually this, but when you visualize, so we use the key. So this is the key. Key is displayed. So apart from this data, we may have some other things. So later on, I will explain the structure of a node structure of a key. Okay, right. So in a binary search tree, a node's left child must have a key less than its parent. Less than its parent. And a node's right child must have a key greater than or equal to its parent. Left child must have a key less than parent. Right child must have a key greater than or equal, greater than or equal to its parent. A very simple idea. Left child must have, so this is left child and this is right child. If we take parent and child, left child must have a key less than the parent. Parent එකට වඩා පොඩි value එකක් තමයි මෙතන තියෙන්නේ. Parent වඩා ලොකු වෙන්න බෑ. Parent උඩින් යන්න බෑ. Left child. Right? Right child is always greater than or equal to parent. Right child can have greater than or equal. දකුණු අත පැත්තේ තියෙන child හැම වෙලාවෙම parent වඩා වැඩි වෙන්න ඕනේ. සමාන වුණත් ප්‍රශ්නයක් නැහැ. සමාන හරි වැඩි හරි වෙන්න. Okay. So in this tree, do you see that? Do you see that? That condition. In a binary search tree, a node's left child must have a key less than its parent. Node's right child must have a key greater than or equal to its parent. Can anyone tell me, for example, let's go with Yasakirti. Yasakirti. Can you see that condition? So can you give one example here? If you take three nodes, if you take three nodes, how you explain that condition? Okay, so you are taking this one, 30, 14 and 39, right? So the left child is 14. So it is less than 30. Yes. And then right child is 39. It is greater than 30. Yes, good, very good. So how about this? 84 and 79. Anyone else? 84 and 39. So 84 is having left child 79. And then no right child. No right child. So then here, just let me know, just tell me whether that condition is satisfied. Condition එක satisfy කරනවාද මෙතන මේ 84යි 79 කියන මෙන්න මේ unit එක. Yes, Vidushan. It is like 79 is less than 84. Like left child has to be less than the parent. So it is satisfied. And then if there are no right child, so then no problem. Right? If there is no right child, that is not a problem. Yes, that's correct. Yes, good. Thank you. And දකුණු පැත්තේ එකක් තිබ්බේ දකුණු අත පැත්තේ හරි වම් අත පැත්තේ හරි එකක් තිබුණ නැත්තම් ප්‍රශ්නයක් නැහැ. තියෙනවා නම්. Right? So if there's a left child must have a key less than its parent. And then if there's a right child, that right child must have a key greater than or equal to its parent. Left child එකක් තියෙනවා නම් තමයි මේක බලන්න. Right child තියෙනවා නම් තමයි බලන්න. Okay. Right. So all the nodes are satisfying this condition here. Like if we take 39 and then 34 is less than 39. 47 is greater than 39. And so on. So likewise, this tree is satisfying this condition. Hence, this tree is a binary search tree. Why it is a binary tree? It is a binary tree because it's having the maximum 2 children. At most 2 children. And then why it is a binary search tree? So it is left child is having a key less than its parent, and all the right childs are having key greater than or equal to their parents. දකුණු අත පැත්තේ ඉන්න පුතා හැම වෙලාවෙම තාත්තට වඩා උඩින් ඉන්න ඕනේ. හා සම ලෙවල් එකේ. වම් අත පැත්තේ ඉන්න පුතා හැම වෙලාවෙම තාත්තට වඩා යටින් ඉන්නවා. So that's the condition. Why that condition has been introduced? So that's where the magic happens, right? Because of this condition, we can have fast searching, right? So if you check any parent node, right? So starting with the root node, if you want to search something greater than this, something greater than this. 53 කියන එකනේ තියෙන්නේ. So we have 53 on in root, right? So if you want to search values greater than that, if you have a value greater than that to be searched, search කරන්න තියෙන value එක ඊට වඩා වැඩි නම්, so then for sure you have to go right side. You can forget about left side. Right? Because of this structure, we can ignore one path, one branch. We can only go with another branch. So if you see like all the nodes right side from 53, right? All the nodes, right? So if we take this subtree, right? මේ 72 කියන එකෙන් පටන් ගන්න subtree එක ගත්තා. So all the nodes, all the keys of those nodes are greater than 53. If you go to left from 53 from root, so all the node below would be less than 53. And අනිත් nodes ඔක්කොම 53ට වඩා අඩුයි. දකුණු අත පැත්තේ තියෙනවා ඔක්කොම 53ට වඩා වැඩි. Right? Right hand side is always greater than 53, or the root key. Left hand side, all the nodes keys are less than the root key. So if you go to another place, like for example, 30. So this node 30, node 30. Node with key 30, right? All the left nodes below 30 are less than 30. All the nodes below 30 are greater than that. So, sorry, all the nodes right hand side of that below are greater than that. Right? So in that case, don't consider other branches, right? Like 30ට පල්ලෙහායින් තියෙනවා කියලා. Below 30 does not mean 61 is actually in the level, it is below 30, but it is in a different branch. It is in a different branch. So now we are talking about only this branch, like 30 is the root and 39, 47, 34, and that area, right? Like 72, 61, 84, those are in a different branch. In the same branch below, same branch below. So is it clear? So because of this condition, that we can have searching like binary search. So if you remember binary search, right? In arrays, binary search in an ordered array. So first we check the middle. So based on the middle, we go left or right. If we go left, we forget about right. We only go one way. So similarly, in binary search tree, when we are searching, we can go just one branch. We can go through just one branch. We can forget about the other branch, half of. So that's why we can have binary search. With trees or binary search trees, with this condition, we can have binary search. So that's why we call them binary search. So we can achieve binary search or search similar to binary search in these trees. And again, like binary search trees, so we can have binary search. And the other thing is binary, right? So these trees can have at most 2 children. Binary කියලා කියන එකේ දැන් අදහස් දෙකක් එනවා. Binary කියලා කියන්නේ මේ maximum 2 children තමයි තියන්න පුළුවන්. ඒකයි binary tree. ඒ වගේම binary search එක මෙතනදී use කරන හින්දා binary search කියනවා. Binary search. Okay. So that's what that's the speciality of binary search. That's the advantage. Okay. Right. So the implementation and other things. So I'm not going to talk today. Right. So I can see your happy faces when I say that. Right. So I'm going to stop at this point today. Right. So then the rest of these slides the implementation, and then searching, insertion, and so on. Those things will be discussed next week, next Wednesday, after the quiz. Okay. Right. And then we can, so we missed the terminology. So I will come back to the terminology and I'll explain those things. Anyway, we will find these terminologies later on, so don't worry. So we can talk about them. If I forget to talk again about terminologies, just remind me. Huh? Okay. So any questions? Any questions up to this point? Or you can ask questions from other slides as well, right? So did you get the idea of the binary search tree? Why we use binary search? The beginning I told you. So we are going to combine fast searching of ordered array and then insertion and deletion. So insertion and deletion. So let's talk about later on how it is easy. How easily can we implement that insertion and deletion? So any questions? Any questions? Anything? So did you get the idea? Akila, did you understand the basic concept of the search? Okay, good. If you have any concerns, sir, එහෙමනම් මෙහෙම වුණොත් මොකද වගේ එහෙම ප්‍රශ්න තියෙනවා නම් අහන්න. මේක මෙහෙමනම් සර් එහෙම වෙන්නේ කොහොමද කියලා වගේ මොනවාරි ප්‍රශ්න තියෙනවා නම් අහන්න. මෙහෙම ප්‍රශ්න අහලා මේ සර් අමාරුවේ වැටේද දන්නෙත් නැහැ. සර් පවුනේ කියලා එහෙම අහන්න නැතුව ඉන්නත් එපා. So if you have questions, I mean, that I cannot answer, that would be the questions that I can learn something. Right? You can මට උත්තර දෙන්න බැරි ප්‍රශ්නයක් අහුවොත් ඒක ඇත්තටම මට හොඳයි. මගේ පැත්තට හොඳයි අනිත් කට්ටියටත් හොඳයි. So we can learn something new. Right? If I don't know something, that means I can learn that. So that's the advantage. Right? So Vidushan has a question. In 30, so 30 means this one, right? This node. Can in 30 can have one child value more than 72. So what do you mean by that? I don't understand exactly the question, Vidushan. Can you elaborate on that? right hand side should be equal or greater than parent. When it's so Vidushan, all right, so Vidushan, so you will ask later. Okay, so Akila, she's having a question. Based on the theory, right hand side should be equal or greater than parent. When it is equal to parent, practically it will repeated. Yeah, it will be repeated. Can we use that parent node to instead? Yeah, I mean, yes. So if you want to insert values, right? Suppose I have a set of values to be inserted, right? I have set of values to be inserted into a tree, right? So suppose the first value would be 10, 50. Suppose the first value would be 50, right? This is the first value I have to be inserted. Second value would be 90. Third value would be 60. So fourth value would be 10, right? Then I have another value 50, right? So then if I insert them from left to right into a tree, right? So the root would be 50. Right? Then the second value would be 90. I have to insert 90. It should go right side because it is greater than 50. The next value would be 60. It should go right side, right? If we insert it here from here, so then we go to right side, but right side we have a value. So now we check with this one. So 60 is less than 90. So then we can insert it here. 60. So now no problem, right? So the 50 right hand side. So we have all greater than that. Right? So then if we insert 10, right? So then where should go? 10 should go. We check first, we check with the root. Root again කොතනද යන්නේ කියලා. කොයි පැත්තටද යන්නේ කියලා බලන්න. 10 should go it is less than 15. So it should go left, right? So then we don't have anything left, so we can add it there. 10 should go here. And then again we have 50. So then we have to check with the root. So root is 50. So that means it is it cannot go, this new 50 cannot go left. It has to go right hand side. But right hand side, so we have 90. Right, from 90, so 50 should go left. So here then from 60, from this one, 50 should go left. Right. So we can have two same values, no problem. Suppose if we change this order, right? Suppose if we change, so suppose this order was different. Right? Suppose 50 is here. 50 is here. Suppose 90 is here. Right. Then anyway root would be 50. And then the next one is 50. It is the same, similar, I mean, equal to the root. So then it should go right. So this would be 50. Then the 60 would be, again, it would be 60 would be here. 10 would be here. Then 90 would be finally here. See? If we change the order, so definitely the tree would be changed dramatically. Because if we want to insert two values, so that does the same value. There are two values there, right? So you have to insert both. So 50, again, the next 50 would be inserted right hand side of the previous. So is it clear? Okay, right. So any other questions? We are going to talk about insertion. Huh? So the steps of the insertion. So I'll discuss this. Okay, so Vidushan, so you had doubt also here, right? Okay, so now it's clear. So good. Right, so I'm going to talk about this one again. So how we insert values. So if you want to insert a new value, right? How we are going to do that? First, we check with the root and we check where we go, left or right. And then if there's the next one, we go where we go, left or right. So likewise, we have one algorithm to insert. Again, algorithm to search, similar algorithm. So likewise, we can discuss those things next week. And remember, so next week, next Wednesday, next Wednesday, 8 a.m. So you will have the quiz. Online quiz. Huh? So you have to do that on LMS. Online LMS. So if you have any problems of logging into LMS and so on, resolve those problems and be ready. If you have any problems like infrastructural problems like the computers, phones and so on, so just let me know. Send me a message. Huh? I'll arrange some. Okay, so be prepared, and then the Viva schedule will be shared next week. Right. Okay, so that's all for today. Have a nice week. See you next Wednesday. Saranko has a question. Can we use mobile phones for is yes. Uh, like if you can log into your LMS with your mobile phone, yeah, so then you can use that. But if you have a computer, I recommend to use that because so you will have more flexibility in that. But uh, mobile phone is also fine. You can if you can use LMS, if you can log into LMS. Right. Okay. So thank you and see you next week.